All right, welcome back. I'm going to do a short clip here called Gyroscopes. I think the book calls it Precession of a Gyroscope, advanced topic. So we had momentum this way, so you had momentum towards you. Let me turn it this way. So the momentum is this way, and as I let go, gravity tries to apply a momentum that way, right? As I let go, gravity tries to spin it this way. If something is spinning this way, the angular momentum is like that. Again, you're spinning this way, orient your fingers with the direction of motion, that's the angular momentum. In addition to the one that's already that way towards that. That's called the L initial. Now, how much torque does gravity apply? We will see that in a moment. I will show you what that is. So here is my wheel. The wheel is held here. I'm holding it by a string here. So this is the wheel, and it's rotating about this axis here. So it's rotating about this axis, like so, rotating like that. So it has an angular momentum in this direction. That's L. Let's call it L initial. Gravity is trying to spin it, so it's trying to give it momentum in this direction. Let me call it delta L. A delta L in this direction. And so the new momentum will be in this direction. That's L final. Yeah, let me call it L final. That's okay. Let me call this angle here delta theta. So once it gives it momentum this way, the wheel will spin by delta theta. But then when it's here, gravity will give it some more momentum in this direction, and then it will spin this way, and then spin this way. So theta keeps on changing. And that's why you saw, let me just remind you again. You saw this. It spins, the wheel spins, turns around. And the theta here I'm talking about is this way. And I want to know how quickly it is moving. It's called omega. Okay? That's what I'm trying to derive here. So here we have a little triangle. Each side is L here. Let me just use the magnitudes. L initial, L final, they're about the same. And this is delta L. Delta L. This is theta. Remember, the arc length, in this case, arc length in units of momentum, arc length in units of radius, it doesn't matter. Still works the same way. So delta L is equal to this length times theta. Just like if you have delta theta, you have, and this is the arc length, delta S, and this is R delta theta, R delta theta is equal to delta S. That's exactly what I'm doing here. Delta L will equal to, I'm calling this delta theta, would be L times delta theta. Okay? That's that. Let me bring it here. Delta L will equal to L times delta theta. I'm going to divide both sides by delta t. Delta t. Delta theta by delta t, I'm going to call it omega, but with a capital omega, to distinguish it from the angular velocity of the thing, of the wheel itself, versus the wheel spinning around this greater circle. So there is the wheel spinning about its own axis, and then the wheel spinning, when I'm holding it by the string, the wheel spinning around the string. So you have two spins. You have the wheel turning and then the wheel revolving. And this is L. Delta L over delta theta over delta t, that's the rate of change of angular momentum. And remember what that is? It's the torque. Just like delta P, delta t is the force, this is the torque. Now, how much torque is there? Let me just simplify this. So this is the wheel, and that's the center of mass of the wheel. The distance here is d, and I'm holding it here. So gravity is trying to spin it this way. So it's applying a torque about this point here. It's applying a torque, and that torque will be the force of gravity, which is mg times d. The angle is 90 degrees, so it's mg times d. So the torque will be the mass of the wheel times gravity times the distance from the center of mass of the wheel to the string I'm holding. And this equals to L times omega. And therefore this omega, how quickly the wheel turns, will equal to m GD divided by L. If L is very large, meaning the wheel is spinning really, really, really quick, omega will be very slow. If L is small, then omega will be quick. And L, I will write L in a moment, what it is. Let me just show you that demonstration, assuming the time is okay. Yeah, I still have a few minutes. So, let's see, I'm spinning it this way, so now it will turn the other way. So L is not that large, so it will spin quicker. Let me do it now much faster. Oh, let me do it this way. I'm holding. If I make it as fast as I can, it should now spin slower. It should turn around, yeah, a little slower than Earth. I don't know if you can tell the difference or not. I think it's slower. Okay. And remember, the angular momentum of the wheel spinning will be the moment of inertia for the wheel times the angular velocity of the wheel about its own axis. So you can write this as the mass of the wheel times gravity times d divided by I, and then omega. And there is an example here in the book that we can do. It says you got a gyroscope in a lecture. It has a solid disc of 120 grams. So imagine the wheel here is not really a wheel, it's a disc. So, and it's 120 grams and 120 grams, 7 centimeter in diameter. So let's say the mass is 120 grams, that's 0.12 kilograms. And let's say the radius of this wheel is, I'm just copying, the radius is, the diameter is 7 centimeters, so it's 3.5 centimeters. So it's 3.5 centimeters, so it's 0.035 meters. Okay, and then D is, it's spinning, the axle is 5 centimeters, so it's being held from the 5 centimeters from the axle. And so D is 5 centimeters. This D here is 5 centimeters. D is 5 centimeters, so that's 0.05 meters. And then they say it is observed that the gyroscope will precess with a period of 1 second, meaning it will make one rotation in 1 second. So it will make. So it will be going around the string by 1 second. So the period would be 1 second. Okay, 1 second. That's the period. So if that's the period, they would like us to calculate how fast in RPM is the wheel spinning. So they say find omega. Okay, find omega. Make sure I copied everything. Okay. Sounds good. So they're saying this. Here's my disk. As it turns, it makes one turn every 1 second. So capital omega will be, it turns by 2 pi this way in 1 second. So that means capital omega is 2 pi per second. 2 pi per 1 divided by 1 second. So that's just 2 pi. Question is, what's omega? Well, what's little omega? So let's calculate it. So we have this. So we will have, we solve for little omega. So little omega will equal to mgd divided by I times capital omega. Okay, so I have mgd. If it's a solid disk, then the moment of inertia 1/2 the mass of the disk times the radius of the disk squared. That's the moment of inertia times capital omega. So the mass simply cancels. So I have 2gd divided by r squared times omega. And now we just have to plug in. So 2, 9.8. D is 5 centimeters, so 0.05. R is, what's the radius of this disk? 0.035. You have to square it times, oh, this should say capital omega. And capital omega is 2 pi. So let me just make sure, get my calculator, where is it at? It's in the back. So we get 2 times 9.8 times 0.05 over 0.035 squared. I got 127.3 radians per second. And I think they want it in RPM. So in RPM, if you want revolutions per minute, multiply by 1 second for every, 60 seconds per minute times 1 rev per 2 pi. So basically, multiply by 60 and divide by 2 pi. That's like by multiplying by 10. So times 60 over 2 over pi. And I get 1216. Let me make sure I compare to the book. Yeah, 1200 RPM. So 127.3 radians, or about 1200 RPM. So this brings me to the end of this really long chapter. And I will see you in the problem solving when we do the homework problems. So we're still not done with it.